All right, we're going to walk through the Chapter 5 review here and kind of work out some of these problems. So here in the first four, it says that solve them using algebra. So you can either use substitution or elimination. Elimination moving forward is probably going to be your best bet. So that's how I'm going to solve all these today. Looking here at number one, we notice that you got different x's, different y's, different everything. You can divide, like if I want to take this one and divide it out by 3 or multiply by a fraction, you can do all of that. But the easiest way here is just multiplying by each other. So if you want to cancel your x here, I'm going to multiply this one by 9, and I'm going to multiply this one by 6. So if I take this one by 9, I get 54x plus 36y equals 108. And then this one by 6, 9 times 6 is also 54. And 6 times 6 is 36y. And then 18 times 6 is also 108. So then we see these are the exact same equations, which means I would have infinite solutions, but we notice up here I have to put it in parametric form. So we're going to let x equal x. And then we take one of these equations and solve it for y. So I'm just going to take this top one, 6x plus 4y equals 12, solve it for y. So you have 4y equals negative 6x plus 12. Divide everything by 4. And you get y equals negative 3 halves x plus 3. So then your y value is your negative 3 over 2x plus 3. All right, this one, I don't like dealing with fractions, so we can get rid of our fractions first. And if you kind of think ahead, you could probably get rid of your fractions and make your coefficients the same, but you don't really need to worry about that. So I got a 2, a 3, and a 2, so we're going to multiply this by 6, which is our common denominator. I have a 2 and a 2, so we'll multiply this one by 2. So here in the top, 6 divided by 2 is 3. 3 times 3 is 9x. 6 divided by 3 is 2. 2 times 1 is 2y. Equals 6 times a half is 3. Here we have 2 times 2 is 4x. 2 divided by, or 2 times a half is negative y. And then 2 times negative a half is negative 1. We could use substitution here, solve this for y, but it is negative. So I'm just going to leave the top equation. So 9x minus 2y equals 3. And I'm going to multiply this one by 2. So I get 8x minus 2y equals negative 2. And because these are the same, I'm going to subtract. So 9 minus 8 is 1. And then your negative 2 minus negative 2 is 0. 3 minus negative 2 is 5. So then I take this x value, plug it back in. So you have 4 times 5 minus y equals negative 1. And it doesn't matter which equation that you plug it back into, as long as it's one that you have. Okay. So you have 20 minus y equals negative 1. If I add y and add 1, I get y equals 21. So your ordered pair is 5, 21. Okay, so those two lines intersect at that point. Here with systems of 3 equations and 3 unknowns, I notice here my bottom equation doesn't have a z. So I'm going to go ahead and take these top 2 equations and cancel my z. In order to do that, I'm going to multiply the top one by 5. And 0 times 5 is 0. And then we need to subtract them. So you have 5 minus negative 1, which is 6x. 5 minus 2, 3y. 5 minus 5 is 0. 0 minus 3 is negative 3. And then you can rewrite this one. But I notice here that I want my x's to cancel. So when I rewrite this one, I'm actually going to take it times 2. So 3 times 2 is 6x minus 2y equals 12. And then we will subtract those. So 6 minus 6 goes away. 3 minus negative 2 is 5y. And negative 3 minus 12 is negative 15. And we will get y. If I divide by 5, y equals minus 3. Okay, so that's y. Now I'm going to plug that back in to this bottom one and find x. So you have 3x minus negative 3 equals 6. Always when you substitute, put it in parentheses. So this becomes a positive, and you're going to subtract 3. So 3x equals 3, and x equals 1. Now you need to find z. So we can take it into the very first original one before I multiplied by 5 and say that 1 plus negative 3 plus z equals 0. So 1 plus negative 3 is negative 2 plus z equals 0. Add 2, z equals 2. And your ordered triple here would be 1, 1, negative 3, 2. Okay, so here in this one, all of my equations have a variable, or have all three variables. And it looks like it doesn't matter which one you want to eliminate. I'm just going to eliminate x's because they have the most ones in them. So we're going to take these two and subtract them. So 1 minus 1 goes away. 1 minus 2 is negative 1y. Negative 1 minus negative 3 is 2z. And 0 minus negative 3 is 3. Then I have to do the same letter on the second equation. But before I do that, I need to take this one times 2. So I get a 2, a 4, a 6, and a 6. So then I'll subtract those two. 2 minus 2 goes away. 4 minus 3 is 1. Negative 6 minus negative 4 is negative 2z. And negative 6 minus negative 3 is negative 3. Now here, we kind of see that these equations are the opposite of each other. And so what we can do here is these are opposite, so we'd add. So negative 1 plus 1 is 0. 2 plus negative 2 is 0. 3 plus negative 3 is 0. So you get 0 equals 0 on this one. So it is infinite solutions, so we need to put it in the parametric form. And with 3 by 3, there's a few ways you can do that. Most often, we will let z equal z. So when we'd have our parametric form, and we're just going to let z equal z, and we're going to solve x and y in terms of that z. They use t as well. So here we've got this equation right here in terms of y and z. So if we take this and solve it for y, we have y equals 2z minus 3. So then in the y spot, we'll put 2z minus 3. And then we can take these values and plug it into this first one and solve it for x. So you have x plus, plug in your 2z minus 3 minus z equals 0. And I put this in parentheses because if this was a negative, you'd have to distribute. So then we need to solve for x. So x plus z minus 3 equals 0. So x equals negative z plus 3. Negative z plus 3. You could, if you wanted to, you could put this in terms of x, kind of like we did this one up here. You could say x, comma, and then go that route. The reason we didn't do that is because we eliminated x from the get-go. But if you eliminated a different variable, you could do it in a different ordered triple. So if you wanted to add in a solution that works, you could just pick a z value here of 1 and then plug it back in. So 2 times 1 is 2, 2 minus 3 is -1, and then -1 plus 3 is 2. So this is an ordered triple where these graphs intersect. Okay, let's look at the word problems here, or these application problems. So, airplane speed. A man flies a small airplane from Fargo to Bismarck, North Dakota, a distance of 180 miles. Because he is flying into headwind, that means against the wind, the trip takes him 2 hours. On the way back, the wind is still blowing at the same speed and in the same direction. So, the return trip only takes him an hour and 20 or hour and 12 minutes, which we don't want minutes. We want everything in hours. This is 1.2 hours. What is the speed in still air and how fast is the wind blowing? So we're going to let x be the plane in speed in still air. So this is x, and the speed of the wind blowing will be y. So we can kind of draw pictures to what's going on. So we're going from Fargo to Bismarck here, 180 miles, and it's going to take 2 hours, and it is against the wind. So you need to subtract your wind variable. Okay, and when I go back, it's going to take 1.2 hours, and it is with the wind. So we're going to add that wind in there. Now, both distances are 180 miles. So 180 equals 180 equals. And this top one's going to be the trip there, and this bottom one's going to be the trip back. And remember, distance equals rate times time, and that's what we're going to use. So the speed in still air times the 2 hours, that will give kind of the distance that the plane would travel without any wind. Okay. But we are going against the wind, so we're going to subtract that same 2 hours times the wind speed. Okay, that kind of slows it down or slows our distance down. It reduces our distance. And then on the way back, we have 1.2 hours times our speed of the plane, plus, because we're going with the wind, 1.2 hours the wind. Okay, so if I were just going my speed for 1.2 hours, I wouldn't get to the 180. I have to take the speed of the wind plus the time of the, or times the time of the wind, and add that to get my 180. Okay, and then we'll take these and solve them. I'm actually going to do this one by substitution because I noticed they both equal 180. So we're going to say 2x minus 2y equals 1.2. Can't do that. Unless one of my variables would cancel, but I don't think that they are. So let's just, if we multiply this one by 1.2 and this one by 2, they should cancel. So 180 times 1.2. This top equation is 216 equals 2 times 1.2, 2.4x minus 2.4y. And then 180 times 2 is 360. 1.2, so that's 2.4x plus 2.4y. Now here, it doesn't matter which variable you cancel, okay, because they both could cancel. So if you add, you're going to cancel the y's. If you subtract, you're going to cancel your x's. So let's just go ahead and add these. So 216 plus 360 is 576. If I add these, that's 2.4 plus 2.4, 4.8x, and these cancel. So you're going to take 576 divided by 4.8, and you get x, which is the speed of the plane in still air. X is 120 miles per hour. Okay, and it also wants how fast the speed of the wind. So instead of canceling x's here, if I subtract, I'm going to cancel the x's. Or instead of the y's, now I'm going to cancel the x's. So 216 minus 360 is negative 144 equals 2.4 minus 2.4 cancels. Negative 2.4 minus 2.4 is negative 4.8y. And so you're going to take negative 144 divided by negative 4.8, and you get y equals 30. So the speed of the wind is 30 miles per hour. Okay. This same type of problem can be done with like a boat in a current, like moving down river versus upriver. It's all the same setup. Make sure that your labels are in the same units. Okay. Everything is in miles, everything is in hours, or maybe you want to switch everything into minutes. That's fine too. Your label then would be miles per minute. Okay, or maybe it's feet per hour, feet per second, or whatever. Maybe they all have to be in the same label. Okay, gas station A, well, a gas station sells three types of gas: regular, which we'll say is X, performance, which we'll say is Y, and premium, which we'll say is Z. For those prices, on a particular day, 6,500 gallons were sold. So we have X plus Y plus Z equals 6,500. And it was a total of $20,050. So that's 3 times X plus 3.2 times Y plus 3.3 Z equals 20,050. 3 times as many gallons of regular as premium gas are sold. Okay, so if I take my regular, which was X, that'll equal 3 times the premium. So 3Z. How many gallons of each gas were sold? Okay, so I have this fact here. And what I can do with this is I can take this and substitute it into both of these equations for X, and then I have Y and Z in those equations. Okay, so we have 3. So instead of writing this, we're going to write 3Z. And instead of writing this, we have 3 times 3Z, which would be 9Z. Okay, so here we have this equation would be 4Z plus Y equals 6,500. Now, I could take this and solve it for Y and plug it into here and just have a bunch of Z's. So Y equals negative 4Z equal plus 6,500. So then I have a Z here, so I have 9Z plus 3.2 times your Y value. So minus 4Z plus 6,500 plus 3.3Z equals 20,050. Okay, so distribute this. So 3.2 times negative 4, that's negative 12, negative 12.8Z, 6,500 times 3.2, so plus 2,800 plus 3.3Z equals 20,050, 9Z. So you have 9 minus 12.8 plus 3.3. So that is negative 0.5Z. I'm going to go ahead and subtract that minus 2,800. negative 750. And then I divide by negative 0.5. To get 1,500. So you have 1,500 gallons of premium gas. So there's one answer. Okay, take this back in right here and plug it in for y. So y equals negative 4, 1,500 plus 6,500. So negative 4 times 1,500 plus 6,500. So that's 500 gallons of your premium plus, or your performance plus. And then I can take z in right here and say x equals 3 times 1,500 and get 4,500 for your regular. Okay, so make sure that you label everything. So you got 4,500 gallons regular. You have 500 gallon of plus, and you have 1,500 gallons of your premium. All right, let's look at number 7 here. These are non-linear systems, and they want us to solve them algebraically. So again, substitution or elimination. One key thing to remember is that when you substitute, you want to make sure that your x's and y's, one of them goes away. Okay, so here if I substitute, if I set this equation, both of these are equal to y. So I can say 4 minus x squared equals x squared minus 4. And I'm just left with x's. So we're going to add x squared, going to add 4. So you get 8 equals 2x squared. Divide both sides by 2. 4 equals x squared. And then take the square root. Now, when you take a square root in an equation, you get a plus minus. So you have plus minus 2. So that is 2 x values. So you are going to have a 2 ordered pair and a negative 2 ordered pair when you set this up. So you got to plug both of them in. So we just take y equals 4 minus negative 2 squared and y equals 4 minus 2 squared. Okay, so you get 4. Negative 2 squared is 4, so 4 minus 4 is 0. And you have 4, 2 squared is 4 minus 4, so you get 0 as well. So you get 0 for both of them, but you have 2 different x values. So these two things, and they are actually 2 parabolas. Okay, graphically, if we kind of take a look at these, this parabola, if I rewrite it, negative x squared plus 4, it got moved up 4 and then flipped over. So it looks something like this. And this parabola still opens up, but got moved down 4. So they both got moved the same direction away from the x-axis. One just opening down versus up. And these are the 2 points at which they intersect, okay, which are right here. All right, number 8, we've got looks like a parabola and a line, and those two can intersect at 2 or 1 or 0 points. Right here, I noticed that my y's have the same coefficient. So I'm going to go ahead and subtract these two equations, and these are going to cancel. So you have 1 minus 1 goes away. You have a 1x squared minus, there are no x squared, so you get x squared. Here I have a linear term, but up here I don't. So you have 0x minus 4x, which is negative 4x, equals, I lied. I have this one right here. Now, the problem is it's on 2 different sides, okay? So I need it to be on the same side. So if I move it over here on the same side, I got minus 4x, and then this would be 0. So negative 4 minus 4 would be a minus 8x. And then you have 0 minus 16, which is negative 16. So here we do have this quadratic, and I'm going to move this to the other side. So you have x squared minus 8x plus 16 equals 0. So you need factors of 16 that add to 8. The factors of 16 that add to 8 are 4 and 4. Signs are the same. They're both negative. So you have x equals 4 with a multiplicity of 2 there. Now to find the y value, we just take this x value and plug it back in. So we could say, maybe here in this easy one, y plus 4 times 4 equals 16. 4 times 4 is 16. So you subtract that, you get y equals 0. So your answer is 4, 0. Okay, so that parabola and that line only intersect in one spot. And the last one here, number 9, little bit tricky. Okay, we do have an x squared, we have a y and a y squared. So I want to get rid of these x squareds because they're the same. But in order to do that, I need to multiply this one by 2. So I get 2, 2, and then the 2, and divide by 2, those cancel, so you just get 7. And then we're going to subtract these equations. So 2x squared minus 2x squared goes away. My variables are on the same side, so that's nice. So I have 0 y squareds in the top. So 0 minus negative 2 is 2y squared. 4y minus 0 y would be plus 4y. And then 13 minus 7 would be 6. Okay, so this is a quadratic again. All are divisible by 2. So I'm going to move everything to one side and divide by 2. So you get y squared plus 2y minus 3 equals 0. So I need factors of 3 that subtract to 2, which factors of 3 that subtract to 2 are 3 and 1. Y and y signs are different. The bigger one's positive, so plus minus 0. So here we will get y equals 1 and minus 3. Okay, so I have two different y values. So if I set my ordered pairs up, I have negative 3 and 1. Now I could have more x values than just 2, but at a minimum, this is what I'm going to have. Okay. So then we're going to say plug it into this top one here. And I plugged it into the top one because it's not squared. It's a little bit nicer. So you have 2x squared plus 4 times 1 equals 13. And you have 2x squared plus 4 times negative 3 equals 13. So this is 4, so minus 4. So you have 2x squared equals 13 minus 4 is 9. Divide by 2. X squared equals 9 over 2. And then take the square root. So you have x equals plus minus the square root of 9 over 2. So there are two answers there. And this isn't really in simplest form because you'd have the square root of 2 over the square root of 9. So you got to multiply the bottom by square root of 2 and the top by square root of 2. And then the square root of 9 is 3. So you have x equals plus minus 3 radical 2 over 2. And that was with the 1. So plus minus 3 radical 2 over 2 comma 1. So that's two answers. That's two ordered pairs right there. And then over here we have minus 12. And then we're going to add 12. So you have 2x squared equals 25. Divide by 2. X squared equals 25 over 2. And then take the square root, so x equals plus minus the square root of 25 over 2. Square root of 25 is 5 over the square root of 2, but you can't leave it. We got to do the same thing. So multiply the bottom and the top by square root of 2. So you have plus minus 5 radical 2 over 2. And that was with your negative 3. So plus minus 5 square root of 2 over 2, comma, negative 3. And if you want to write those out in separate ordered pairs, you can, or we can just leave them like this. But it is, these two things do intersect at 4 different spots. And this one, we haven't talked about this equation yet. We will in the conic section, but this is a parabola and kind of a different equation there. I'm not going to tell you what it is yet, but we'll get to it in the conic section. All right, we're going to stop there for this video, and then we'll pick up the rest of the problems in the next video. All right, let's get in here to the second part of the review. So the first part we went 1 through 9. Now we're going to look at 10 through the end. And we're going to start here. All of these are solved by graphing. So remember when we graph systems, we're looking for their intersection or where they overlap. Okay, so here on 10, just looking at the equations, we have 2 lines. And there's a multitude of ways you can graph these 2 lines. You can set them both to y equals mx plus b, or you can find the intercepts. With this one, I think it's going to be easiest to find intercepts. So we want 0, comma, some number, and some number, comma, 0. So if x here is 0, this part goes away, and you divide by negative 3. 12 divided by negative 3 is minus 4. So you have 0 minus 4. And then if y is 0, this whole term goes away, and you're going to take and divide by 2, so you get 6. So 6, 0, which is not on here. So we'll go off just a little bit. And then we can connect those lines right there. Okay, you could do the same thing here with this one. But let's just go ahead and solve this one for y and see what we get. That way you get 2 different methods. So I'm going to add x, so I get 3 over 2y equals x plus 4. And then I'm going to take and multiply by 2 over 3 the whole side. So you get y equals, you have to distribute that. So 2/3 x plus 8/3. Okay, so 8/3 is a little bit over 2. So 2 2/3. And then you're going to go, you can go down 2. So 1, 2, and left 3. 1, 2, 3. So we have something that looks like this. Now, these don't actually intersect on my graph, but we don't know that they're parallel. I know that the slope of this one is 2 over 3. The slope of this one is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So it's 4 over 6, which is 2 over 3. So these two have a matching slope. So in that case, there is no solution for that system. They don't ever intersect. Okay, here we have a system of nonlinear equations. We have a parabola and a line, and these are actually inequalities as well. So we're going to be shading. So let's start with the easy one, the line. And I know I have a solid line here. We're going to start at positive 3, closed circle, and the slope is 1. So we're just going to kind of go up 1, right 1, or down 1, left 1. And I like to go all the way across my graph. That way I get all the exact intersections. Solid line. Okay, and you want the y values that are bigger than your line. So that would be shading above. Okay, now the next one is in a little bit different form. So we have y less than negative x squared plus 9. So this is a parabola that got flipped upside down and shifted up 9. Okay, so if I go up 9, and there were no, oh, and it's an open circle. There were no stretches or shrinks or anything like that. So it's the same parent function ordered pairs. So if it's upside down, I start at 0, 0. Then I go 1 away on both sides. Then I'm going to go 2 and then 4. Again, open circles, mirror image there. So I just counted 2. 3 and 9. And then we have 4, 1, 2, 3, 4, and 16. So that's 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 1, 2, 3, 4. And the other one won't be on there. And it is a dotted line. And we want the y values that are less than your parabola. So that would be below. Okay, so where your graph intersects is actually right in here. Okay, so we have a dotted parabola part there, so you can't choose anything on that curve. You can choose the items here because that's a solid line. But like this point here at negative 3, 0, you can't choose that because it's on a dotted line. All right, here we have a system of 3 equations that we want to graph. And this one's already solved or 3 inequalities. This one's already solved y equals mx plus b. Open circle dotted line, so positive 1. And then the slope is 1, 1. And you can just do a hashed line there. Make sure you're careful and you stay with the slope. And you want y values bigger than that line. So we're going to shade above. Okay, this one, it's a solid line. We can do intercepts there. So I want 0, comma, number, and a number, comma, 0. Okay, so if x is 0, you get 6. And if y is 0, you get 12. Well, 12's not really on there, but 0, 6 is. And 12, 0, we'll see, it's about there. So my slope is negative 6 over 12, which is negative 1/2. So I can go down 1, right 2, down 1, right 2, down 1, right 2, or up 1, left 2. Just making sure that that line is falling. Okay, and with this one, you could test a point. I know some of you like that testing a point method, especially if it's in this form. So if I test 0, 0, all of this goes away, and 0 is less than 12. So that means I'm going to shade below. Okay, and the last one here has no y value. So we're going to move this one to the other side. So x greater than negative 1. So that's actually a vertical line, negative 1, dotted line. And you want x is bigger than that. So we're going to shade to the right of it. Now, it might be kind of hard to see here, but my answers come in this area. And remember, you have dotted lines and a solid line. So if a question says pick a value, it's best to pick an obvious value. Like I wouldn't pick -1, 0. You can't because they're on dotted lines. But even like this point right here, don't pick that one. Don't pick this one that are on both lines. That's not an obvious solution. Okay, number 13 is another nonlinear. And we actually have some harder graphs here with this nonlinear. And you can remember the transformations, or hopefully you remember some transformations. You could also use a table of values to graph. So if you don't know how to graph something, I encourage you to make a table for your work. Okay, so this is an absolute value. And this absolute value went left 2. It got flipped over the x-axis and went up 2. Okay, so remember the absolute value starts at 0, 0 and kind of goes up and to the right and up and to the left. It's that V. Okay, I didn't stretch or shrink anything, so it's still going to have a slope of 1 and -1 on both sides. So we went left 2, over the x, which that doesn't happen, and then up 2. So 1, 2. Now it's upside down, so it still has that slope of 1 and -1. It just got flipped upside down. Okay, again, we're going all the way across my graph. There's no shading on these because this is equations here. Okay, logarithm. This logarithm went left, so log base 3 of x is the parent function. It went left 3 and up 2. Now, remember with the logarithm parent function, it's the inverse of your exponential. So this side is -2, -1, 0, 1, and 2. And then this side would be like your 1/3, your 1/9, 1/3, 1, 3, and 9. Because if it was the other way, it'd be your exponential. So we're taking these points and moving them left 3 and up 2. So if let's just start here at 1, 0, 1, 0. We're going to go left 3, 1, 2, 3, and up 2, 1, 2. So they actually intersect right there. Okay. 1/3 -1. So we're going to go left 3, 1, 2, 3, up 2, 1, 2. And you also have that vertical asymptote that goes left 3. So it was at 0. So 1, 2, 3. So you have this vertical asymptote. So this side's going to go like this. Maybe not so close. Let's try 3, 1 here. 3, 1. So left 3, 1, 2, 3, up 2, 1, 2. So then this is going to go this way, like that. So your intersection here is -2, 2. You can definitely check this on a graphing calculator, but make sure that we see work on your page on how you graphed it. So that's negative absolute value of x plus 2 plus 2. And then your log, doesn't look like I could do it on this calculator. Let me grab another calculator. So negative absolute value of x plus 2 plus 2. And then your log base 3 of x plus 3 plus 2. And then if we graph those, okay, we can see our intersection right there, and we can calculate that intersection. Just kind of go over close to it. And it has -2, 2 right there as our intersection. Sometimes you may want to zoom in a little bit closer because there could be two intersections there that you're not quite seeing. Okay, here's linear programming. Find the minimum and maximum values of the given objective function indicated by the feasible region. So here's our feasible region, and you have this ordered pair of 4, 0. You have this one of 0, 5, and you have this one of 0, 2. So I like to make a table, and M is your objective function. So we have 0, 5, 0, 2, and 4, 0. So when I plug those in, I have 200 minus x minus y. So this one's 195. 200 minus x minus y, 198. And 200 minus x minus y, 196. So this one would be your max, and this one would be your min. So we're looking at the vertices of your feasible region. Okay, so here's a full-on word problem with this. So we have to graph and find our feasible region before we can test the values. So making furniture, a furniture manufacturer makes wooden tables and chairs. So we could say, like, I don't know, maybe tables is X and chairs is Y, or you can say T and C. The production process involves two basic types of labor, carpentry and finishing. A table requires 2 hours of carpentry and 1 hour of finishing. A chair requires 3 hours of carpentry and a half hour of finishing. The profit is 35. Okay, so here's our objective function. Profit equals 35 per table and $20 per chair. The manufacturer's employees can supply a maximum of 108 hours of carpentry. Okay, so let's find an equation right now for carpentry. So if we look back up here, a table requires 2 hours of carpentry. So we have 2 hours for the table for carpentry, and a chair requires 3 hours of carpentry for a chair, equal or is less than equal to 108. And then, and 20 hours finishing per day. So for finishing a table, that requires 1 hour, so 1T. And a chair requires half an hour, and that needs to be less than equal to 20 as well. Now, it wasn't said in here, but we can assume that T is greater than equal to 0 and C is greater than equal to 0. So the number of chairs and the number of tables that you make has to be 0 or more. You can't have negative. So those are two more constraints that are there. How many tables and chairs should be made each day to maximize profit? Okay, so what we need to do is graph these. And let's see, I'm going to put a stamp down here for my graph. Okay, so we're going to put all of these, let's say that this is T and this is C. Okay, this could also be your X and your Y. If you want to go ahead and change all of, that's a Y. If you want to change all of these to X's and Y's, you can, but we will be in the first quadrant here. Okay, So if I solve all of these for C, which would be my Y, let's just go ahead and change all these. We'll say T was X, X, Y, Y, and then X, Y. Okay, so if we solve all these for Y equals mx plus b, so we're going to subtract X. So 1/2 Y less than equal to negative X plus 20. And then multiply everything by 2. So Y is less than equal to negative 2X plus 40. Okay, so I probably need to go by tens. So 10, 20, 30, 40, and down 2. So 20, 40, 60, 80. So I go down to 1, 2, go right 1. So it looks like we have this graph right here. And we want Y to be less than that, so we're going to shade below it. I'm going to just put an arrow to which side I'm shading here. Okay, this one, we're going to subtract the 2x, so 3y less than equal to negative 2x plus 108. Divide everything by 3, so less than equal to negative 2/3 x, and 108 divided by 3 is 36. Okay, so this is 20, 30, and about 36 there. And we're going to go down to right 3. So 1, 2, 1, 2, 3. So it's about something like this. And we're going to shade below that. So right here is our feasible region. Okay, now it can be a little bit hard to find where the vertices are. I have 1, 2, 3, 4 vertices. So if I make a table here, so I have 0, 0. I have 20, 0. I don't need this one out here. I have, this one was 0, 36. That was using the y-intercept. Now this one out here, I don't know and I need to find. Okay, in order to find it, I need to solve the system of those two equations. Okay, well, I have them both in y equals, so I can set them equal to each other. So negative 2/3 x plus 36 equals negative 2x plus 40. Okay, so subtract 36, add 2x. Okay, so negative 2/3 plus 2 is 4/3 x equals 40 minus 36 is 4. So we're going to multiply everything by 3/4. So x is 3. And then we plug that back into one of the equations. So y equals negative 2 times 3 plus 40. So that's negative 6 plus 40, which y is 34. So that's another ordered pair. So 3, 34. And if we plug those back into these equations right here, it should equal 20 and equal 108. So let's look at 2 times 3 plus 3 times 34. 108. And we have 1 times 3 plus 1/2 times 34, and we get 20. So our system was solved correctly. Now we're going to find the profit, which was this equation right here. So we're going to plug x and y into that profit equation. So if I plug 0 and 0 in, I make 0. We have 35 times 20 plus 0, 700. And we have 0 plus 20 times 36, 720. Whoop. And then we have 35 times 34, or sorry, times 3 plus 20 times 34. 785. Okay, so this right here would be our max, and that is at 3. Let's see, we made tables as x, 3 tables, and 34 chairs. And we have a max profit of 785. Okay. So make sure you set up your equations, graph it, find the vertices, and then make your table to maximize or minimize, or maybe it wants both. Okay, kind of like up here. Sometimes we're not bounded by the x and y axis, so we want to see minimum and maximum if 0, 0 wasn't an option. All right, that is your review for your test. If you have questions, feel free to reach out.